Well, how about some more fun with equilibrium constants? Doesn't that sound like a blast? In any case, when you manipulate an equilibrium equation, it's pretty easy to change up the constant based on these few simple-ish rules. For example, if I have an equilibrium written left to right, but switch it forwards to backwards, can you imagine what happens to the equilibrium constant? Based on the law of mass action, or writing these equilibrium constant expressions, it says this goes on top and this goes on bottom. So this will go on top instead of on the bottom, and this will go on the bottom instead of the top. And so, was that the mathematical name for that reverse process? The upside down is reciprocal, isn't it? So, for example, just like this, the new constant equals the reciprocal of the old constant. Or if you have a number, here's the initial equilibrium equation at a particular temperature. This constant is 2750, implying to me that it favors the product. But if I write the equilibrium equation backwards, then of course the new constant is, drum roll, the reciprocal of 2750. In other words, a small number. So I guess that makes sense. If the forward reaction has a large constant, then the backward reaction has a small constant. They're reciprocally related, if I can enunciate that properly. Or what's up with this one? Here we go. So here's the original equilibrium, I think it was our original equilibrium equation and the constant. What if I just took this one times 3, this one times 3, and this one times 3? 3 and 3 and 6. What would happen here? Well, I guess it would be hi in the numerator to the 6th power, I2 in the denominator to the 3rd power. So in other words, it's this same old constant to the power of 3. I guess you could prove that to yourself, something like this, eh? So this thing cubed gives me this thing. Or indeed, if you had numbers, do the same thing. So whatever term, by whatever multiplicative term the entire equation is taken by, then this is to that power. So if I divide it by 2, divided by 2, divided by 2, or times it by half, times it by half, times it by half, do I times this by half? Not exactly. Don't I raise it to the 1/2 power? Did I say that? Did I do that? Did I write that the correct way? I did. There it is. So whatever factor an equation is multiplied by, the constant is taken to that power. Interesting. To the 1/2 power, do you remember that means the square root? That's kind of silly. So in this one they give me equilibrium concentrations of N2, H2, and NH3. What's the value of the constant? Well, this is not along the same lines. It's even older than that. But if I have this concentration and this concentration and this concentration, don't I just plug those values into my law of mass action expression to find a value? So I'm getting a feeling I might have to use that constant 0.605 in a question to come. We'll see. Maybe not. So the equilibrium yada yada has a constant that's fairly small. The pressure constant looks pretty small. And then have partial pressures of gases here. An equilibrium mixture contains a partial pressure of 0.55 HOCl, so that's 0.55, and H2O is 1 atmosphere. What will be the value of the partial pressure of the Cl2O, dichlorine monoxide? Again, this isn't necessarily a manipulate the constant example, but it's a good example, I suppose, of how if we know all the variables except for one of them, 0.09, 0.09, 0.09. 0.09 was the constant. I know the partial pressure of this gas. I know the partial pressure of this gas. I can solve for the partial pressure of that gas. Given the equilibrium and corresponding measured concentrations at 600 degrees, the temperature matters, but it doesn't enter into our calculations. I know if I made it warmer or colder, the constant would change. But if I have these equilibrium concentrations, so I would write the equilibrium constant expression with this squared in the numerator, this in the denominator and this in the denominator squared. Then if I were to look at the reverse equation, so SO3 is now over here, SO2 and O2 are over here, but it's also been multiplied by 2. So let's fiddle with that. So here's my original equilibrium concentrations. SO3, square it, O2, SO2, square it, and find a constant is 4. Oh, concentration? Yeah, molar concentrations. All right, that's right. But the equation I was given then was actually the reverse and double. So when everything's multiplied by 2, I take the square. So I took the reciprocal to reverse the equilibrium equation, and if it was doubled, I square that value. So what's the reciprocal of 4.315 squared? Small. Interesting. I'll leave it at that. So cartoons, yay cartoons. So I have an N2 molecule, an O2 molecule equilibrium with 2 NO2 molecules. Looks like that's a balanced equation. Assume the cartoon is a representation of the molar concentrations. So I can't see these particles, but if 1, 2, 3, 4, 5 relative units, maybe 5 moles of O2, and 1, 2, 3, 4, 5, 6, did I get that right, of NO, and 1, 2, 3, 4 relative units, perhaps 4 moles of concentration. Determine the value of the equilibrium constant. So, yeah. Oh yeah, I think I counted these correctly. So if I had 6 of the NOs, 5 of the O2s, and 4 of the N2s, molar representative of the molar concentrations, how about a constant of 1.8? And I just got these 6, the 5, and the 4 from counting this cartoon, assuming the cartoon that I can imagine seeing is representative of the macroscopic amounts that I can actually weigh. Oh, no way, I threw this in here too? How fun is that? Let's do it. How do KP and KC relate to each other? Yeah, they might be equal. This one might be equal to this one if this comes out to 1. R is the gas constant that we studied in Gen Chem 1 when liter atmosphere is moles per mole Kelvin. T is the Kelvin temperature, and delta N is the change in number of gaseous moles, products minus reactants. So if I look at balanced equilibrium equation, this says I have 2 moles of gas over here, 1 mole of gas here, and 2 moles of gas here. 2 here and 1 more here is a total of 3 moles of gas. So if I go ending minus beginning, it's 2 moles of gas here minus 3 moles of gas here. 2 minus 3 is negative 1. So my delta N in this case will be negative 1. I was given the constant Kc, and I'm trying to find Kp. So I had 3 moles of gas over here, 2 moles of gas over here. We have to pay attention to the gas phase or whatever. And then the Kelvin temperature was 600 Celsius plus 273, changed to Kelvin, 873 Kelvin. The delta N was 2 minus 3, that's a negative 1. 873, that's a constant given to you, and that was given to you. It turns out that it's a fairly small pressure constant, equilibrium Kp pressure constant. Interesting. So the change in the number of gaseous moles is the key in relating Kc to Kp. Use the Dalton's law of partial pressures we learned a long time ago in Gen Chem 1. It just says the number of particles is, Avogadro's principle says the number of particles is proportional to the pressure. And so, find the value of Kp. I have one of these. It looks like, actually, it's PCl5. This is PCl3 and Cl2. Is it balanced? Yeah, it's balanced. Okay. So I have, in the numerator, I must have 1, 2, 3 relative units of pressure of this. 1, 2, 3, 4 relative units of pressure of this. And these would be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. Did I count that right? 9 relative units of PCl5 in the denominator. Yeah, I got that right. And they're all 1s in the balanced equation, so there's all to the 1 first power, and Kp equals that. Well, if Kp equals that, what's Kc equal to? Yeah, so Kp was 1.33. The gas constant is 0.0821 liter atmosphere per mole Kelvin, and Kelvin temperature is 300 Kelvin. Assume that's a warm room, warmish room. Whoa, I didn't give the answer. Nice. That leaves it for you guys to figure out. What's Kc if I have Kp and I know this and I know this? Cool. If you can't figure it out, come check it out with me sometime. Thanks for watching, guys, and I'll see you all too soon.